Hi, welcome back to Mechanics and Control of Robotic Manipulator. This particular lecture is actually like slightly different because we are taking the mobile robot and we are actually like trying to derive the equation using what we have learned so far. So what we have learned, the robotic manipulator is a you call multi-body approach, then the Danavitt-Artenberg approach we have used for even deriving the kinematic and dynamic level. The same philosophy we are trying to use it for the mobile robot, that too like a land based mobile robot, how that would be work here. So in that sense what we are trying to indent here, so the kinematic and dynamic model derivation of a land based mobile robot using Danavitt-Artenberg approach. So in that sense we are trying to see how to derive the kinematic model, that too up to velocity level, then we will come back to the dynamic model, then we will end with the dynamic motion control. So if that is the case, what we can see, so the mobile robot I can show as a small, you can say rectangular box, because it's a land base, so it can be plotted as a small, you can say planar object. So now even we can actually like take it in a mechanics point of view, it is a planar joint. So planar joint means it is actually like 2 translation and 1 rotation would be possible. So now if I assume that there is a inertia, or you can say initial frame, which I call I. So this initial frame I consider as a reference, can I actually like refer the mobile robot? So obviously yes, but in this case there are n number of points within the mobile robot, how we can actually like choose. So for that we assume that there is a body frame which is associated with the body or the mobile robot, which is consist of xb, yb and zb are the coordinates, or you can say coordinate frames. So now can I actually like define it? Yes, we can do this a simple, you can say the spatial description manner, where we can consider the rotation about, you can say rotation of B with respect to I, we can write as a rotation matrix of B with respect to I, and the position vector of B with respect to I we can write, and then we can come back with the transformation matrix and then so on, so we can do it. But if that is the case, so then you can see like the derivation of what we have come up with here is not possible, because that is straight away everything is a rigid body basis. But if we talk about what you call Danavitt-Artenberg, so there are several constraints are coming. What are the constraints? So you can see like Danavitt-Artenberg says that every link should be a binary link, in the sense only 2 joints are possible for one body, but in this case it is actually like 3 joints, that too like one, you take one body, so ground to 1, then 1 to 1, like that it keep goes, but here it is not like that. So second consideration, every joint supposed to be 1D of joint, but it is a planar joint. So obviously you have to do some kind of modification for the frame arrangement. So we cannot take it straightforward like RB with respect to I and PB with respect to I, that may not work in Danavitt-Artenberg approach. So for that what we are trying to do, we are trying to bring the coordinate what we need to know. So here you can assume that inertial frame to body frame, which is actually like we can write as a position vector, which is nothing but x and y, because it is in a plane. In addition to that, the ZB you can see and ZI are you can say parallel, but the XB and XI are actually like non-parallel. That angle what we call heading angle, or you can say yaw angle, whatever you can call it, so which is actually like come as a psi. So now if you talk about the coordinates or the variables in terms of Danavitt-Artenberg, so in the sense here there are 3 joints. So one is actually like x translation joint, y translation joint is the second one, and the z axis rotation is the third joint. So now we want to write it this in the Danavitt-Artenberg approach, or for that first we have to draw the frame arrangement. So how we can do the frame arrangement? I can see that there are 2 translation and 1 rotation is coming. So I can assume that so in order to make it the life comfortable or life is easy, I assume that y axis translation as the first joint, which is Z1, and the x axis translation I take it as a Z2, which is second, and the third axis eventually it is end up with the body frame, which is I am considering as the Z3. So Z3 is actually like a coincident with the B. Okay, so these are the 3 joints which are active. So now what I am trying to see from the initial frame, which I assume that this is the initial frame, from the initial frame how this goes one to another. So now I want to derive as a Danavitt-Artenberg approach. So for that what we need to know, so you need to know like where the x axis coming. So the x axis I can actually like make it, the first x axis which is x0 or xi can be written in that way. So where it would be the perpendicular to the plane containing z0 and z1. This is what we learned, right? So in that case, what you can draw, you can actually like draw this line, so which is actually like the plane containing you can draw. So in that sense, you can see this is the you can say forward direction of x0 or xi. So once you obtain the same way, you can go for x1. So the plane containing z1 and z2, the perpendicular to that, so it can come upward or downward. I took it as a upward direction as x1. So similar way you can go, z3 and z2 are a plane containing on the screen. So now the plane piercing probably the x2 or coming outward can be x2. I have taken coming out as the x2. Now x3 I can choose as per my own, because there is no preceding link. So I can choose as a simple where it is parallel to x0. So in the sense x3 and xb are parallel. Now coming to the screen, where we can actually see the same thing what we derived, I put it here just to derive the Danavitt-Artenberg parameter. So here there are three variable y, x and psi. Okay. So now based on this, what I can derive the Danavitt-Artenberg parameter. We can actually like see again alpha k minus 1, in this case alpha 0. So alpha 0 is actually like rotation about x0, where z0 parallel to z1. So you can see this, it is actually like rotate 270 degree, that is why it is 3 pi by 2. Further you can see that the theta k, in the sense theta 1 here. So you can see like x1 and x0 are actually like you can see minus 90 or 270 degree rotation about z1. So like that you can actually like derive all other you can say joint where 2 and 3. Once you derive, what you can do, you can actually like go back, you can say MATLAB, or you can write it in the ARM matrix and you can derive the individual transformation matrix, and then you can actually like multiply it, you can say post multiply, and you will get the final kinematic model. Then you can go with the you can say angular velocity and the linear velocity, then you can get the differential kinematics. So for that, what we are trying to do, we are trying to do the MATLAB base, which is we have seen in the very second week of the course. So that is what we are trying to show here. So in the sense, we are trying to derive the kinematic and dynamic model together. So first we are writing the general DH parameter, which is alpha, d, a and theta. So further, based on this particular system, so it would be having psi dot, right, psi double dot, then x dot, x double dot, y dot, y double dot, which we have written here. So y double dot we have written as y dd dot, or you can say d dot. So similarly x double dot I have written as x dd dot, psi double dot actually like written psi dd dot, okay, like that. And here how many joints? So there are 3 joints excluding ground or excluding 0, it is actually like 3 joints. So based on that, we can write the DH table which we have obtained there. So we have incorporated the DH table, then we can actually like see what you call the general Danavitt-Artenberg, which is we call non-standard one, that is we have written it here. So then you can see like we are building the transformation matrix for each joint. We are substituting individual DH table row wise, substituting into the individual transformation matrix, then that would be you can say freezing it into a cell. So here the cell which is A, so A is consist of 3 subcells, so that is what we call A of I within the braces. So based on that, what we can do the direct kinematics in the sense forward kinematics, which is nothing but post multiply with the further matrices, in the sense T01 first, then T12, T23, like that you can keep extending. So that is what we have done here based on the for loop. You can see like this is actually like doing it. So once this is done, what you can do is, so you can actually like first identify the individual transformation matrix T01, then T12, T23. After that, you are trying to find out what is T03. Okay. So T03 here I have written as T01. So then you can see the position vector and the orientation vectors all coming into a picture. Once these all done, what we can do, we can go for velocity kinematics. For that, you need to know individual rotation and position vectors. So that is what we have obtained here. So once we obtain this, then we can use the angular velocity propagation, so which is actually like straightforward. Here you can see the first 2 joints are you can say linear joint, then it is very simple. The third joint is actually like rotary, that is also we have done. The same extension we can do it for the linear velocity propagation. The first 2 joints are linear joint, you can see that y dot and x dot is added here, and then we can go across, right. So similar way we can find the end effector velocity and angular velocity and linear velocity. So once these done, we can go the same way for the angular acceleration propagation and what you call velocity propagation. Before that, I just want to plot what is the individual matrices and what is the final end effector can say position with respect to base, which is fulfilling. You can see the position vector x and y and the orientation, which is actually like psi. If we take the tan inverse, then you can see psi is the case which is the orientation angle about the z. These all actually like fulfill. So now what one can see, we want to derive the dynamic model. For deriving dynamic model, what you need to know? You need to know the angular acceleration, the linear acceleration and the centroidal linear acceleration. So we will do the forward propagation. For finding the centroidal linear acceleration, you need to know the centroidal location. So here there is only one body exists, right? So although we have taken 3 virtual links, but only one physical link is there. So in the sense, the centroid we consider only the third body, where the B frame and the centroid is actually like away. We assume XBC and YBC is the, you can say, x axis and y axis coordinate. So based on that, we can actually like derive the what you call the linear velocity propagation in the forward. So in the sense, first we calculate the angular velocity. So angular velocity, you can see like you can see the cross product, which is actually like coming as what you call simple gyroscopic effect, and then you can see the angular acceleration of that particular joint. So like that you can do it. So now coming back to the linear acceleration. So linear acceleration is actually like straightforward, where you can actually like do it a1, a2, a3. So once you obtain, then you can actually like go back the centroidal linear acceleration here, the third body. So that is what we can actually like do it here, right? So now I hope once you calculate the centroidal linear acceleration, so what one can actually like expect, the initial force, right? The initial effects you need to actually like come back. So the initial effects what you have, so here you have initial force and initial moments, right? So what are the initial force and moments? So F3, which is actually like M3 multiply with AC3, where M3 here only one body, which is actually like you can see, which is just M, and here we assume that it is in a plane. So in that sense, it is having only centroidal moment of inertia, that too z axis only, second moment of inertia only there. The product of inertia we assume to be 0. So then you can see the initial moment we can calculate. Once you calculate, then you go across the joint forces. The final joint doesn't have anything else because there is no end effector added. In the sense, F3 would be simple initial force, whereas N3 would be small n3 would be capital N3 plus this what you call F3, which is acting on the centroidal, right? That would be generate the couple. And when we come backward, so F2, F1 and F0 can be calculated in this way because it comes from all the cases. Since there is no body, physical body, so that is why it is just a transpose, or you can see just the rotational operator added. So the similar way you can come to the joint moment. So N3, I said small n3 is a capital N3 plus the moment or the couple generated by the initial force. Then you can come backward N2, N1 and N0, where F0 and N0 are the shaking force acting on the ground of the body, similarly shaking moment acting on the ground based on the body motion. So now we will go to the input vector. So here we have to actually like get the first two joints are actually like linear joint, then the forces, the third component of the force would be equal to tau 1 and tau 2. The tau 3 is actually like the rotational, so moment third component would be tau 3. But what you can write Fx, Fy and Fz, sorry Mz you have to write, but here the tau 1 is equal to Fy and tau 2 equal to Fx. So we have to actually like modify it. Before modifying, you can see like the dynamic model, we can write it in a state space form in this way, where we can use the simple MATLAB command equations to matrix, where we can actually like take the coefficient of this x double dot, y double dot and psi double dot, and you can see like I have interchanged already, this is Fx, this is Fy and this is Mz. The same way we can actually like make it n vector, where this multiply with this would be the coefficient and m that would be subtracted, that would be the other effect. I hope now you are actually like clear. So we can actually like go to the MATLAB and then you can actually like see, okay. So now we come back to the MATLAB window. So you can actually like see this is what we have seen. So initially, just to make comfortable, everything is actually like clear. Then we are actually like defining the individual transformation matrix, you can say variable alpha, d, a, theta. Then you can see the state variable depend on the system. So here you can see psi, x, y, psi dot, x dot, all those things are coming. And as per the DH table, we have written all the cases, whatever we have obtained based on the frame arrangement. This is the DH table. Then we can actually like get the non-standard. Then we can actually like come back with what you call the individual transformation matrix. Then you can get the final direct kinematics. And I want to show this. Then you can see like the final position vector and orientation vectors, all I am trying to show. Then coming to the velocity kinematics, for that individual rotation and position vector supposed to be known. Then the angular velocity propagation, okay. Then the linear velocity propagation we have done. Then we are coming back to the centroidal linear acceleration. For that we are coming back this. So here we have added the, you can say, inertial effects. So then we are coming to the angular velocity propagation. So then the linear velocity propagation, then the linear acceleration of the center of mass. Then we are coming back to the inertial force and moments. So here only you can say F3 and N3 would be coming. Then the joint forces we have calculated as such. Then the joint moments. Then we can actually get the tau 1, tau 2, tau 3. Then we can rewrite the M and NV like this, right. So now if I run this, so what I can do, you can see like if I run this, so I will get a benefit. So just to show that I am just skipping to the what you call MATLAB window, you can see like these are the output which we are actually like obtained. So you can see like this is the individual transformation matrix, this is the DH table, and this is the individual transformation matrices, right. And this is the final end effector matrix with respect to base frame, and this is the position vector, and this is the, you can say, normal, sliding, and you can see approach vector, and this is the final, or you call end effector angular velocity with respect to base, and this is the end effector linear velocity with respect to base, and this is the end effector angular acceleration with respect to base, and this is the end effector linear acceleration with respect to base. So like that you can actually like get it. Then you can get the tau 1, tau 2 and tau 3. These are the three value which we needed, but this is equal to Fx, this is equal to Fy, and this is Mz. So then we derive the, you call, inertia matrix, and then we have actually like get the other Fx or other vector, which is actually like you can do it a Newton-Euler approach with the rigid body method, the same equations which will get, the same thing we derived it here. So now we will go back to the MATLAB window itself. So where we are actually trying to show the dynamic model. So for that I will just show the slide, then we can actually like get understand. So these are the outcome. So these outcomes actually like can be written as the M of q and N of q comma q dot, and this is the way we can write the final dynamic model. So once you derive the dynamic model, what we wanted the control aspect, right. So before that I just want to show what is Fx, what is Fy, and what is Mz. So these are the values which you can actually like see it, which we have derived in the MATLAB. Even you can do it in by hand, but MATLAB is easy, right. That is what we have seen in the regular course. So based on that we can go for the control aspect. Even before that you want to make a dynamic model, then this is the dynamic model relation, where q double dot double integrate, you will get q. But right now we are interested in the control aspect. So in the sense, if I see the tau based on the desired and the model parameter, this is the case. So now we can try even two different control just for demonstration. You can see the computer torque control we can use, which is very popular in our course. Similarly the PD control is the other popular. So here there is no gravity coming, that is why it is a simple PD control, because it is a land based mobile robot. So based on that what we wanted to write a controller code. So we can actually like see, for that there are several segments. I just want to show one simple segment where we are actually like having a via point. So if it is a via point, what you can see, there is a two segments will come. So individual segment we can do it. In that case, even in the motion planning or trajectory generation, we have seen there are two sub cases. One is with via point velocity specified, then it is a two independent segments, right. So that is what we can actually see, where the via point velocity specified. So this is the equation which we have derived, that can be portrayed in a MATLAB. So this is the way we can portray. Similarly, the trajectory 2, which is actually like you can write as a third order polynomial, but you can see via point velocity is not specified. So then you can see this will give 8 cross 8 and 8 unknowns, and then you can do it. The same way we can actually like write it in a MATLAB code. So these all actually like we have done. Then what we can do, even some cases we want to do this, you can say simulation, we can actually like make it this. So for that you can see the same Euler method we have used. The vehicle mass is 30 kilogram and all other cases we have given, and you can see these are the trajectory generation. For that we have considered the, you can say, trajectory boundary conditions, and then this is the first you can say via point case where there is no velocity specified. Then this is actually like with velocity specified. Even further you want to go with a circular profile, can we actually like bring it the circular trajectory details. So once these all obtain, we can actually like do the numerical integration. So you can see like for that, so we are actually like taking two segment. So T of I which goes up to T0 to TV, that is the first segment, and then TV to TF, that is the second segment. So this is what we have done. Then we come back to the desired values based on the circular trajectory if I want to do it. So this is a simple circular, right, where Rx is the radius. If Rx and Ry are different, then it will give a ellipse, okay, and similarly omega x and omega y are different, then that would be giving different profile. We can see in a MATLAB. So right now we can actually like see this is, we assume the circular trajectory. So now based on that we can actually like see that we can go for the circular trajectory cases also. Then we can come to the system dynamics. System dynamics required Jacobian matrix just for further end. So then you can see like so NV underscore mu and d mu we have got it. Here actually like it not supposed to be called d mu and n mu, because here mu and q are same, okay. So that way we can actually like get it. Then we calculate the error just for you can say position and the velocity error. Then we can actually like go for the tau. So then you can see like it is a simple computer torque control, or we can go for the velocity control. You can see the same thing, right. So based on that we can actually like go for the system update, then the acceleration calculate, then time velocity, time update for the velocity, and the position update, which is the second velocity update. Then we can actually like plot as an animated view where the box is moving, because we have considered the rectangular box as the vehicle, right. So that is what the case. So now we can actually like go to the MATLAB window where I already opened it here for your benefit. So you can see like this is the dynamic model code. In fact here I already made the controller code. So you can see like this is the mass value, this is the inertia value, it need not to be 0.1, even you can substitute different value, but I have taken a rough, and I assume that the centroid and the body center are actually like same, that is why XBC and YBCs are 0. And then initial condition I assume that the vehicle starting from 0 with a 0 orientation. Then we can actually like see that the trajectory coefficients are given, and we can actually like generate. So right now I am actually like trying to see the first case, which I am actually like trying to see that the you can say trajectory with via points velocity is specified, okay. So in that case, so I am actually like making the circular profile are actually like subdue. So I am just commenting this. So I am just commenting this. So then we can actually like see that this is actually trying to follow what you call this via point. So you can actually like see what via point I have given here. It is really tricky. So you can see like x displacement at via is actually like 2 and y also 2, but the second point, which is the final point, x axis there is no displacement, and y is actually like 4. In the sense it is actually like V shape, in the sense you can say it is actually like greater than or equal, or in the sense greater symbol. So that is what we are trying to see. I will just try to run it first. First of all, it is running or not, we can see. You can see this is with two segment, in the sense the end point velocity is 0, and you can see it goes and it is actually like goes backward, right. So you can actually like see it is actually like making it. So there is a switch over happening, right, because it is ending. But you want to make it this in a mobile robot, it is not really preferred. You want to actually like smooth. So for that what we are actually like trying to do, so we are actually like trying to make a smooth profile. So that is what I said, via point velocity is not specified, in the sense the initial what you call, so initial you can see velocity of the second segment is the final velocity of the first segment. Similarly, initial acceleration of the second segment, we assume the final acceleration of the first segment. So, second segment initial and final would be match with the first segment. That is what the idea. So, in the sense the second profile we take. So, now in that case, so if I run, you can see like the same via point would be maintained, but you can see that the profile itself smooth. What is the via point? It is 2, 2, which is actually like fulfilling, but what addition? The vehicle is actually like making a smooth profile, right. So, this is the beneficial of the even the trajectory generation which we have generated, because in the manipulator it is not very clear, but the vehicle profile you can see it is very important, right. So, now you can see in the error case it is actually like one pulse only, right. So, whereas in the other case you can see like there are 2 pulses have come, right. So, this is what the idea began. So, now even you want to give a circular profile. So, I assume that there is a circular profile we want to indent. So, I assume that the circular radius are actually like equal. So, I will just see that is actually like happening here. So, the circular radius is equal and the frequency also equal. So, in the sense it is supposed to follow a circular profile, we can see whether it is actually like happening or not. Okay. Now, you can see it is actually like line of sight also we have used. So, in the sense it is actually like following on the line. So, this all actually like happen, right. So, these all the whole idea behind the Danavet-Attenberg approach. So, now you can see even the mobile robot can be used in the case of what you call in the sense of you can see Danavet-Attenberg approach, we can derive the equation, and even we have done the motion control. So, here we have done the you can see motion control with the computer torque control. Even for the mobile robot, even simple PD control is sufficient. So, just to demonstrate, you can see already the PD control is executed. Now, I am actually trying to show the computer torque control performance. So, you can see then the performance is actually like little more improved. So, that is what I just wanted to show it. Okay. So, now you can see like this is a computer torque control performance. So, I hope you have enjoyed. The whole course is actually like given a whole idea, and this particular lecture is actually like a recap of whatever we have seen from the beginning to the end. That is what the whole idea. So, now even if you look at the error, so error earlier it was actually like 0.01 or something, now it is actually like 10 power minus 5. That is the beauty of what you call model based control. If your model is very accurate, then you can go the classical control like a model base. So, that is the whole idea behind here. I hope you have actually like got the whole essence what we intended this particular lecture. So, with that I am actually like ending here. So, see you then, thank you, bye.